Greetings. Come right up on in. Get up on in here. You want to do anything special over the weekend? Anything exciting in your life you want to share? Anything going on? Decorated for Christmas already? Well, I guess it's about that time. People start as soon as they can. I'm a little tempted to start, but I won't. I'll wait till Thanksgiving. Your family got a new car. Oh, cool. What kind of car is it, Mackenzie? New car is always exciting. Everybody wants to go for a ride for a while, until it gets a little bit. Oh, 4Runner. All right. That's a very popular. It's a good one. That is exciting. Yeah, we had a Halloween party on Saturday at my cousin's house. We went over there and had some chow, had some candy, played some games. Well, we played a game, and I really don't know how to describe it because it's not a board game. My cousin, he's into this type of gaming to where like he'll travel to like Nashville or something, and they have a big conference center rented, and he goes in and he takes just a bunch of stuff with him. He takes these totes, he has them shipped or whatever, and he has like all these little figurines. And he likes the war gaming more than anything, so he'll have all these little tanks and soldiers and everything, little miniatures that he's painted, little airplanes, and they'll be accurate to the time. If it's going to be a World War I battle, he'll have World War I airplanes and tanks, and if he's going to be American troops or British troops or French troops or whatever, he's got French tanks and English tanks and American tanks, and so it's all very specific to be accurate. And they have these great big tables that are like bigger than pool tables, and they set up little houses or set up buildings and all. And you draw these cards. It tells you how far you can move, and you move this airplane or that tank, and they do war battles basically with all these little figurines. So that's kind of what we did. He plays a lot of our games with us, so the family decided we'd play one of his games with him. So he simplified it. He made up his own rules, and he had some little Star Trek figurines from the original Star Trek. It's like we beamed down to this old Western town and had a mystery to figure out, and had, we moved those little figurines. I don't know. I don't even know what you call that kind of gaming, but that's what we did on Saturday for our Halloween party. Whatever it is. We're still missing like 5 people in here. Well, we're not going to be able to wait forever. But all right. Some of you, not all of you, some of you, I have emailed a little form to you with one question regarding the quiz that we had last week. So we're going to talk about that next Monday. So fill out that one question. I think I know the answer. I'm waiting to see what you'll tell me. But that's not everybody. Just some people got that. So some of you have not done last week's quiz. That's another issue. A lot of you have done the quiz, did great. Some of you aced the quiz. Several of you aced the quiz. Got it all. So that's good. You're understanding. But some of those that didn't ace the quiz, I just had a question. So, all right, I'm going to put this up on the screen. Which jack-o'-lantern are you today? 1, 2, 3, and 4. Give you a chance to kind of sound off there. Tell me where you're at today. Sid's a 3 today. Woo! Yelson's a 1. Nice. I'm kind of a 4 today, I think, at this point. Maybe a little 3-ish, just in the fact that trying to get my brain working this morning to feel a little like, woo, it's early. The bed was very inviting this morning. It's like, oh, you can stay with me today. I see lots of 2s on the screen. 1 because of Christmas, because Kellen's got her Christmas decorations up, so she's all number 1. Lots of 2s. That's a 2s. That's how my eyeballs kind of feel like number 2s. Just like, okay, we just go back to bed. No, can't. All right. So no 4s in here, but we got some 3s, a couple of 1s, several 2s. All right, nice. Just checking to see where you're at there. All right, let's look at where we're at in algebra. Let's see, 0B. We're right over here. Let's go to our grade screen as usual, just to kind of check in on everything. Yep, we are done with the quiz. You should be through 3.06, and almost all of you are. Just a couple of folks got to get a couple things turned in. Almost there. So this week, November 5th is Sunday, so we have graphing polynomials and a practice test, which means next week is the test. So I'll get that test opened up here real soon. I'll get it on the screen because it should be up there by now. It's not, but I'll get it on there. So we have one lesson this week, graphing polynomial functions, and then that practice test. And I will show you. Let me go back to the activity screen. We're down at the end of module 3. I have Mr. Brock takes the module practice test. I have the video. So after you take the practice test, if you struggle with parts of that, you don't understand why it's wrong, check out my video, because I take the exact same practice test and I explain every problem as I work it. So if you get like the first 10 right, don't watch the first 10 questions of my practice test. It's like, I don't know, 40 minutes, 35, 40 minutes. You don't have to sit there and watch the first 10 problems if you knew what you were doing and got those right. You don't have to waste your time watching something you already know. You can, but you can also just fast forward until I'm doing number 11. If you're like, number 11, I was lost. Okay, well, let's fast forward the video and watch number 11. So it is there for you to use as a tool to help you prepare for the test. Because if you get like a 30% on the practice test, you miss a whole bunch of them. You need to do some reviewing before you jump into the test, because it's a pretty good indicator that if you bomb the practice test, you're probably going to bomb the test. But we'll talk more about that next week after you've done the practice test. So, all right, we're going to look at our one lesson, 3.07. So click on there. Oh, here we go. All right. Oh, we got to watch this little dorky video. Hold on.
Meet Patrick. Wild World Amusement Park hires him to build rides. One of the park's main attractions is Loch Ness, an extremely fast roller coaster that goes underwater. There's just one problem though. There has not been much rain lately, and the lake that the roller coaster dips into is drying up. The amusement park owners have asked Patrick to rebuild the section of the roller coaster that goes underwater so that it goes even deeper. First, Patrick removes the section of the roller coaster that goes underwater. Next, he makes a sketch of what the new section should look like. Now he must direct his employees to build the new piece. But how does he describe a shape that curves up and down like this? These types of shapes are the graphs of polynomial functions. Patrick knows that a graph with two curves like this is a cubic function, so he can begin figuring out the equation to give his employees. The next time you see a function like f of x equals a number times x cubed plus a number times x squared and so on, think of the graph as a roller coaster.
All right, that's pretty crazy. That's pretty crazy. It's pretty crazy. So would you ride that roller coaster? Anybody gonna ride that one? I love roller coasters. But he said it's really fast and it goes underwater. So when you hit that water, it's going to be like hitting a brick wall. I don't want to hit water really fast because that's going to hurt. But yeah, that's never going to exist in real life. But that's just kind of a funny little thing. But no, it's got a good point. It's talking about the shape of the roller coaster in that one section looks like an x to the third equation. So we're going to talk about graphing polynomial functions without technology. And we're going to talk about it with technology too, so don't panic on me here. So graphing on the coordinate plane is kind of adapted, right? Because you started out just graphing a line. All right. We start out with just points first. We first learned how to graph a point on the Cartesian graph, the XY coordinate graph. So we did points, and then we did lines, and then we did parabolas, which are from quadratics. And now we're looking at higher degree polynomials. So if you need a review on graphing a line, you had an equation that was a y equals mx plus b, which in this case was 1/2 x plus 5. And you would make a table. Remember that? You'd make a table, an xy table, and you would put the x's into the equation to find out what the y values were. So this shows -6, -4, -2, 0, and 2 for the x values, because there's a 1/2 in there. So they want it to be nice numbers on the right side. So they skipped and just did even numbers. And ended up with these points: -6, 2, -4, 3, -2, 4, 0, 5, 2, 6. So then they could take those and put those on a graph. And then when you do that, connect them, you've graphed a line, right? So we could do that. The other thing we learned to do after that is just get the y-intercept and the slope and make some points and connect it and do that. But you've graphed a line for years. You've done that 4 or 5 years now. So that is a nice review if you want it. There's also graphing a parabola, quadratic equation. You haven't done that as many years, but you can do that a lot the same way. You can find the vertex, this -b over 2a. If it's in standard form, where it's ax squared plus bx plus c. So you can find what the x value of the vertex is. You can substitute that in to get the y value. So the vertex is at 2, -1. So that helps you figure out the numbers for your table. Since the vertex is at 2, you select numbers on both sides of 2 for your table. Substitute in to get your y values. So now you've got your ordered pairs, and you'd graph your parabola. All right, so you put in your 0, 7, 4, 7, 1, 1, 3, 1, 2, -1, and graph your parabola. So again, that's review stuff that you've done in the past. But we're talking about higher degree polynomials now. Like a cubic function is a higher degree. F of x equal x to the third. So if we're graphing f of x equal x to the third, you can do it along the same ways. You can choose x values and make a table. So this is just saying, okay, for x to the third, I'll just take -2, -1, 0, 1, 2. Substitute those in there. -2 to the third power, -2 times -2 times -2. That'll give you -8. See, so there's the x value substituted into the x to the third power equation. And you've got this table, x's and y's. Then you plot those points, and we get an x to the third. This is the parent function. This is just no translations, no modifications. This is just straight up x to the third, right? It goes through the origin, and it has a origin symmetry. If there's 1, 1, there's -1, 1. If there's 2, 8, there's -2, -8. So those have the opposite points around the origin. So, and let's talk briefly, because we're going to be looking at this time, on how functions can be translated. So let's look at translations when you're doing things. And this works with most functions, all functions here. If we put in x plus c, in fact, let's just look at this on paper. Let's play just a little bit with this. No, let's do it on Desmos. That's quicker and easier. We'll start with that current function. I'll just make it y equals for Desmos. Okay, so there's the same function we just looked at. It's got 0, 0. It's got 1, 1. Well, if I get right on it, got the 1, 1. There's a 1, 1. Got -1, 1. I'm going to change this. I like to take off the minor grid lines, because that puts a whole lot of extra lines that I don't really care about. And I like to make it go by ones. So that way we've got just a standard graph. Which, by the way, is it this lesson? Yes, right at the beginning of this lesson, by the way. It has, if you have a printer at your house, you can print graph paper. You click on that link right there, the very first sentence, and there's graph paper for you. So you can print out graph paper right here, the very first sentence of the lesson. So I've printed out some of that to use. But we're going to talk about transformations again. So the first transformation we'll talk about is, I'm going to put X in parentheses just so we can play with it. About when we just add a number on the end. If I add +3 after the X to the third, what's that going to do to our graph? If I just put a +3 on the end. Remember, we got different things that happen. Graphs go left and right. They go up and down. They get skinnier and wider. All kinds of different things that can reflect up and down. So McKinsey says it moves up 3 if I add a 3 on the end. Well, let's add a 3 on the end. +3. Absolutely, it does. We'll put that original one on there just for comparison. The blue one is the original X to the third. But if we put +3, it's going to move it up 3. In the same fashion, if it's a -3, it moves it down 3 instead. So we know what happens when we add a number on the end of an equation. That's not a big mystery. But what about if we put it with the X? We're going to put a -3 inside the parentheses. X -3 to the third power. It's going to be in parentheses. So the whole X -3 is going to be raised to the third power. That's not going to raise it up, right? Or lower it down. -3. If I put -3, it's not going to bring it down because we know I have to put it after the variable to go down. -3. Oh, McKinsey is not fooled. -3 makes it go right. Remember, inside the parentheses with the X does the opposite of what we think. We think -3, oh, that's going to move it down to -3. No, it doesn't move it towards -3. It moves it to +3. The turning point of this equation, which was at 0, 0, is now at 3, 0. It moved it to the right. So it does just the opposite. If I put +3, it moves it to the left. So we can see the difference between the +3 and the -3. All right, what if I just take the 3 and put it out front? In front of the parentheses. It's not being added or subtracted to the X. It's being multiplied times the equation. That's a little tougher to think. So if I put the 3 out front, watch what happens. Oh, look at that. The red one is the one with the ×3. What happened was this point on the original equation that was 1, 1, we substitute 1 in for X. I'm going to label that point. There it is. Gets multiplied by 3. Now the point 13 is on the graph because you substitute 1 in. Instead of it equaling 1, we multiply it by 3. And so it gets exponentially faster. It goes up faster. It gets skinnier. It's skinnier. If I make it a 10, you'll see it even skinnier. Oh, see, now it's a 10. Instead of 13, 110 is on the graph. It's way up here. Because now we multiply it where it's going up 10 times faster than it was. In the same fashion, if I make it 1/10 or 1/10, I can put it as a decimal, 1/10 instead. They get 0.1. Now it gets wider because of it, instead of it being a 1, 1, it's at 1.1. See, it's got this point now because it brought it down to where it's only 1/10 of the size it used to be. So when we put numbers, and if we make it a negative number, right, if we make it a negative number, it just reflects it downward. See, now it's going up on the left and down on the right. I could take away that 0.1 and just make it a -1, just a negative out front, and it just reflects it downward. And I say reflects it downward because it's not reflecting over the x-axis unless that's the turning point. Let me show you that. Let me put the +3 on it. If I put it +3 and then put the negative out front, it just reflected it downward, but it's still way up here. It didn't reflect it over the x-axis. That would be totally different. It reflects it downward. So that's what's talking about with these shifting functions. If you put a plus inside with the x, it moves it left and right. If we put a plus c or a minus c after it, that's going to move it either way, up or down. And this, the cx multiply, it causes it to be wider or narrower. And then it talks about out front, makes it wider or narrower again. But it also talks about if c is negative, it will reflect it. Well, it says over the x-axis, only at the original x to the third. It's flipped upside down. It's flipped upside down. Not necessarily over the x-axis. That's kind of, I don't like the way they said that. Because if we've done some of this other, if we've done some of these other things, you'd see that. So, all right. So they want to graph the cubic function x plus 2 to the third power. All right. We're going to do this on paper and kind of look at it together. X plus 2 to the third power. So to find where the vertex is going to be, where is that turning point? Where's the middle of the graph? Let me make that 3 a little better. We can take the x value in the parentheses and set that equal to 0. Solve that. So x equals -2. Where x is at -2 is going to be the turning point of this graph. So that's what we want to base our table on. When we do x and y and make a table, we want -2 to be in the middle. So we'll put -3, -4, -1, and 0. Just because we figured out from the x plus 2 that it's moved over 2, and that's where the center of the graph is going to be. So let's base our numbers around that. -4 as an x. -4 plus 2 would be -2. -2 to the third power. -2 times -2 times -2. -2 times -2 is +4 times another -2 is -8. So we have the point. -4, -8 is the point on our graph. -4, -8. There's one of the points on our graph. -3. -3 plus 2 is -1. -1 times itself 3 times is going to be -1. So we have -3, -1 as a point on our graph. -2. -2 plus 2, well, that's just 0. So 0 to the third power is still going to be 0. So -2, 0 is on our graph. -1 plus 2 is a +1. -1 in for x. -1 plus 2. +1 to the third power is a +1. So -1, +1. And then finally we have 0. 0 plus 2 is 2. 2 to the third power. 2 times 2 times 2. +8. So we can see our graph starts down here, rises quickly, slows down, makes that turn, then starts rising quickly again. So there's our graph of x plus 2 to the third power, which we expected that because we already talked about on Desmos. If we add 2 to that, it's going to shift it left 2 units. And that's exactly what I did. So this was, we were graphing it without technology. We didn't use Desmos to help us here. This was just graphing it, just making a table. We knew this was going to be the center of it because the x plus 2 made x minus 2 the center. And so we were able to graph points on both sides of that. So they end up with the same graph right there. They go through the same process, but there's the same points that we used, -4, -3, -2, -1, and 0 for our x, and graphing that. All right. Then they look at a quartic function. Quartic. That's x to the fourth power. Let's look at like x to the fourth plus 3. We'll do something a little more complicated than that. X to the fourth plus 3. And we can graph it on the same graph we put over here. So x to the fourth plus 3. So since this x, there's nothing with the x, that means the center of it is going to be at the 0, x equals 0. So we'll just do a standard -2, -1, 0, 1, 2 table. So -2 to the fourth power. Ooh, this is going to be off of our graph, but we'll do it anyway. -2 to the fourth power. So -2 times -2 times -2 times -2. So we got -2 times -2, which is 4. And we got -2 times -2 is 4. And 4 times 4 is 16. Yeah, that's going to be way up off our graph. -1. Oh, plus 3. Plus 3. I didn't add the plus 3 at the end. So that's actually 19. -1. So -1 times -1 is 1 times -1 is a -1 times -1 is 1. Since it's 4 of them, it's going to be back to a positive 1 plus 3. So that's at 4. 0 to the fourth power is 0 plus 3. 1 to the fourth power is 1 plus 3. 2 to the fourth power is the same as this. It's 16. It's a positive plus 3. Notice, since it's a quartic function, we end up with the same numbers. But let's graph what we can graph here. All right, -219. That's going to be way up here somewhere, way up off our paper, way up the top. And as well as the 219, way up off our paper. So we know those points are gone. -1, 4. -1 right here. 0, 3 is right here. And 1, 4. And the next point, before it gets to the 2, is way up there. So if we graph that, we'd start way up off of our graph. And since it's a fourth, it's going to come down pretty flat. It almost makes it a U instead of like a V. And then goes up again really fast. It's not quite a parabola because it's flatter on the bottom because of the fourth. But that's what our graph's going to look like on x to the fourth plus 3. It's just x to the fourth, but it's raised up 3. Kind of like we expected to do. Let's look at that. What I'm talking about being flatter than a parabola. Let's get rid of these. Y equals, here's a parabola, right? There's a parabola. It looks a nice even shape there. This is even also, but it's differently. Look, it's flatter at the bottom. See, that is different than a parabola. It gets flatter because of that fourth degree. If you make that even extremely more, let's make it x to the 14th. No, see, the 14th gets even flatter still. These are not all equal. It is still going down. If you zoom in and in and in, we can see that the point here, 0.073, this is 0.16. See, it is going up. 0. It is slowly going, but it slowly goes up on that blue one. Takes a long time for it to get a very big number at all. See, we're not even at 0.3 yet. So it takes it a while. Where this is getting quicker. This is, it still shows it as a 0 on the Y because we're not zoomed in enough. Let's see if we can zoom in enough to where it's not a 0 anymore. Desmos may not calculate it that small. Still shows it as a 0. It's not. It's a really, really small number because 0.1446 to the fourth power is a very small number. Yeah, we're not going to get in here far enough for it to get it off to 0, is it? Oh, there it is. 1.752 times 10 to the -12th, which means in front of that 1 is 11 zeros, and that's where the decimal should be. 0.0000000, 11 zeros, and then a 1. That's how small of a number it is. So, all right, but there's our graph. Get back out where we can see something here again. Woo. We zoomed away in there. All right, there we are. All right, now we're back to something we can see. So yeah, that's x to the 4th plus 8. So we can do all of this without technology. We can easily make a table. If we know what an x to the 4th looks like, we can just do the translation of moving it up 3. We have lots of options there. Make an xy table. So most cubic and quartic functions be this simple to graph? Well, let's look at some more polynomial functions right here in their link. So linear graph. What do you notice about the two ends of the graph of a line that has a positive slope? Well, the right end is going up towards infinity and the left end is going down towards negative infinity. If it has a negative slope, it's the opposite. The left is increasing towards the positive values. The right is going down to the negative values. All right, so that's the linear graph. Quadratic. Let's look at the two ends of a quadratic. If it's a positive, both ends, left and right, are going towards the positive infinity. If it's a negative in front, if it's a negative equation, it's going towards negative infinity. Go back to the cubic. What about the ends? End behavior is important in learning how to graph something. For a positive cubic equation, it's going down towards negative infinity on the left and up towards positive infinity on the right. If it's a negative, it's just the opposite. Positive on the left, negative on the right. Quartic. Same as a parabola. If it's positive, both ends go towards positive infinity. If it's negative, they both go down. Here's a different quartic function. Still, it's got multiple turning points, but still, it's a negative quartic function, and both ends go down. It won't change the ends. So you may notice a pattern there. If the highest degree of the exponent, this is a second degree, this is a fourth degree, those are even numbers, both ends are going to do the same thing. With odd numbers, both ends do opposite things. And that holds true. Here she's going to graph x to the 3rd plus 2x squared minus x minus 2 using just some key points that she already has. So let's look at that. So she has x-intercepts of -2, 0, 1, 0, -1, 0. Y-intercept of 0, -2. And she has the equation, which is x to the 3rd plus 2x squared minus x minus 2. So given that information right there, maybe you won't be given these. Maybe you'll say the zeros. Zeros are -2, 1, and -1. That's the same thing. The zeros, that means these are the points. -2, 0. -1, -1, 0. 1, 0. But she's given these points. If you have the x-intercept and you have the y-intercept and you have the function, you can graph it. You don't need any more information. Now, again, this is a sketch of a graph. This is just great. We're not graphing it, we're sketching it. There's a slight difference. So let's look at this. We'll take these points, the x-intercepts, and graph those. -2, 0. That's right there. 1, 0. That's right there. -1. Right there. And the y-intercept is down here. Now, what we know is this is an x to the 3rd, and it's positive. So we know the graph is going to look like this. So this is going to be going up. This is going to be going down. Because it's odd degree. 3 is an odd number. So we know ends do opposite things. Since it's positive, we know it's this way. Since we have the y-intercept, we know it goes down here. We know it comes back up to there and must turn and go back there. We can fill that in because we know where it crosses the x-axis. We know where it crosses the y-axis. Now, I said this was a sketch because this is not actually accurate. When we do this on Desmos, just to see, you're going to see this is actually a little steeper. This actually goes below there and is coming back up. And I'm not sure on this one. That one may even go up further, but I remember on that one. Let's put this in Desmos just to compare. X to the third plus 2x squared minus x minus 2. That's better. Okay, it doesn't make it up to the 1, so that part's about right. But notice it goes lower than the y-intercept over here. And when we sketch it, usually we just go through the y-intercept. That's the lowest point. It wasn't. It's actually a little lower. This is a little taller than it really is. See, it doesn't go quite that close to the 1. But that's okay. This is 100% fine as a sketch. It's good because it shows you overall what it looks like. This side goes up, this side goes down, it crosses to those points. That's all we need for a sketch. If we're doing this by hand, we're not doing it with technology. This is a perfectly acceptable graph. In fact, it's great. That's a great graph because it shows the end behavior. It shows that it's rising, increasing, decreasing, increasing. It's got the correct points. That's what you're looking for when you do a graph without technology. And so she'll do that there if you want to watch that video. So, this is good. Without using technology, and I'll let you put this in the chat. In the chat, guys. Let's get some participation here. Make sure you're awake. Describe the end behavior. That's all we want to know about this graph. This is 4x to the 23rd power. So we want to know, what does the left end do? Does it go up or down? What does the right end do? Does it go up or down? For a 4x to the, I'll even make that bigger on the screen if you're having trouble seeing it. Get down here to it. There it is, 4x to the 23rd. Up and down. Which is which? Are you saying left is up and right is down? We know it goes up and down. It is odd. But when you're talking about the end behavior, tell me what the left end does. Tell me what the right end does. The left does this. The right does that. All right, I'm seeing left down, right up. Sid disagrees. He says left is up. So we've got both ways now. All right, we've got some disagreement. Okay, it is the 23rd. So I like what I'm seeing as far as we know the ends are going to be different. They're not going to go the same direction because it is an odd number. They're not going to go the same direction. So to determine which way they go, we have to look at the coefficient. Is it positive or is it negative? Well, that 4 is obviously a positive 4. There's no negative out front. So since it's a positive with an odd, the left, we'll do 4x to the 23rd. All we have to put is the 4x to the 23rd. The rest of it doesn't matter. Left goes down, right goes up. If it was a negative, it would turn it over. Down, negative turns it over. And we can put the rest of it, negative 5x. This just makes more turns when you put the rest of it in there. See, it makes more turns. That's the negative 5x squared, negative x plus 7. So that just affects the y-intercept and where it turns. But still, the left goes down, the right goes up because it is a positive. So that's the only two things you need to look at. What's the largest exponent? Is it even or odd? Right, the largest exponent in this case is odd. So that tells us one side goes up and the other one goes down. And to figure out which side goes up and which side goes down, is the coefficient of that largest exponent a positive or a negative? It's a positive, so the left goes down, right goes up. All right, good job. Thank you, Sid, for providing a counterpoint for us to discuss. Get this back up here. Check answer. It's not necessary to graph this. That's correct. All you have to do is look. 23 is an odd number, so that means the ends will be in opposite directions. And because it's positive, the left end will go down, right end will go up. So there you go. Check your answer. And look at this chart for a function's end behavior. Here you go. This is great for your notes right here. Great for your notes. You could print this page off. You could put this in your notes. End behavior of a graph. So I know there's problems on the test. There's problems in this week's assignment to describe the end behavior. So you're looking for something like this. When it's asking you to describe end behavior, you're talking about both ends, left side, right side, left side, right side. If they both go the same direction, you don't have to say left and right. You can just say both. Both go up, both go down. But you have to talk about the two ends. Don't just say it's an odd degree. Well, okay. Do you know what an odd degree does? You told me it's an odd degree. That may be correct, but you haven't told me what the ends do. Tell me what the ends do. And this is not sufficient. The ends travel in opposite directions. Okay, well, that may be true, but which ones go up, which ones go down? Do you know? The answer you have to give is on the bottom row. So odd degrees are these first two. If it's positive, they go this way. If they're negative, they go this way. Up, then down, down, down. Even degree, even's a little easier because we know quadratic's pretty good. If it's an even, we know both ends are traveling the same direction, and they'll go up unless it's a negative, and then they'll both go down. So there's a little end behavior chart for you. All right, see what the next page holds for us. Now it lets us use technology. With technology. So here's the things to keep in mind. It says you may need to customize the view, right? Showing the axis, the grid lines, min, max value. See, that's what I do over here. I go up here and I make sure I turn off those minor lines because look at all those lines it puts in there. I turn that off. I don't care about that. You can turn off the grid, but that's worse. You want the grid. I want the axis numbers. You can turn that on and off. Arrows, you can put that on or off. That's just like this axis, the x-axis. Look when I turn arrows. Now there's an arrow in. That's fine. That's just personal preference. It doesn't really matter. X-axis. See, you can turn the x-axis off. No, we want the x-axis. But you can customize the view. You can say, I just want to see from negative 10 to positive 10. See, so it goes from negative 10 to positive 10. So you can change things like that. But now the X is wider than the Y, so it's not really square anymore. So that's kind of weird. So you may not want to do that. But just showing you can customize it. And you may need to, just so you can see your graph better. And you know that you have to use the little caret sign to do to the degree, third degree. You got to put the little caret in front of it. So it says, okay, so it tells us to graph this function using technology and then describe the end behavior. So I'm just going to copy that. I'm going to go to Desmos. Now, when I paste it, it messes it up because it doesn't put the exponents. But if I highlight that 4 and do that shift 6, oh, look, it made it an exponent now. Highlight the 3, shift 6, highlight the 2, shift 6. So now that's what the graph looks like. Describe the end behavior. Well, we can graph it and see it, but we should have already had it in our head that it's an even function, so we know both ends are going the same direction, and it's a negative, so they're both going down. But it's always nice to graph it and double check yourself. Even if it wants me to do it without technology, I can do the problem, but I may want to double check my work by graphing it. So this is wonderful. Now notice, just as an aside, not really part of this lesson, but we're going to talk about it a little bit. This is a fourth degree. That means there's 4 zeros. There's 4 solutions to this equation. But when we graph it, we only see 2 zeros at 0.709 and 1.64. That means the other 2 are imaginary zeros. So it does have 4 solutions, just 2 are imaginary because they don't show up when we graph it. All right. So you can see the description of the end behavior is correct. Far left and far right continue down. Same graph that we just did on Desmos. Here's another one, negative 3x to the third. So this is an odd degree, and it's a negative. So this is going to be left up, right down. Again, there's only one real zero. The other two are imaginary. They're complex because it only shows 1 0 when we graph it, when it should have 3 because it's a third degree. All right, let's go over here. Okay, the x-intercept of any linear or quadratic equation is found by substituting 0 for y and solving it, right? Solving it for x. Here's another review on that. If you need to review more on how to find the x-intercepts, this is just a linear equation. It's just an x. It's not an x squared. It's not an x to the fourth. It's not an x to the seventh. So you can just solve this, put 0 in for y and solve it, and that'll tell you the x-intercept. And then when you graph it, you see, oh yeah, 4 is the x-intercept. See, it crosses the x at 4. With quadratic functions, it's not as easy. You'd have to factor it or use the quadratic formula. There it is with the quadratic formula to get the two x's. X equals 2, x equals negative 3. And when you graph it, you see x is at 2, x is at negative 3. Graphing, it's often the easiest way to find it, but if it turns out it's imaginary zeros, there's no x-intercept. But if they just want the x-intercepts, if you want the solutions, you may not be able to find them because it may be imaginary. But if you just want the x-intercept, you can see that one graphing. All right. This one, using graph technology, you can find the x-intercepts. This crosses at -1, +1, and 3. The graph crosses the x-axis 3 places. Substitute the coordinates each point in the function, replacing f of x with y to check the solution. Oh, to check them, yeah, we would put -1. If we substitute -1 into the equation, we should end up with 0 because that's what the y equals is 0. If we substitute 1 in, we should end up with 0. If we substitute 3 in, we should end up with 0. All right, and then there's more examples if you'd like that you can click. And this has approximate the real number solution. Real means not imaginary, which means if you graph this, you may have 4 real solutions, but you may find out there's less. So that when you graph it, oh, here's the graph. Turns out there's only 2 real solutions. The other 2 are imaginary. And it says give them to the nearest hundredth. Well, since their graph doesn't give us any values, we can put that in Desmos and get it to the nearest hundredth. Again, y equals, and I got to make those exponents again because it does not copy and paste well. Okay, there's the same graph. What's it to the nearest hundredth? So this x solution, to the nearest hundredth, we've got to round it because hundredth is 2 decimal points. So negative 0.51. And the other solution is 2.31. Negative 0.51, 2.31. That's the 2 real solutions. The other 2 solutions are imaginary. That's the 2 real solutions. And we can just graph it and get the solutions. Nice. Since they only ask for the real number solutions. So, adjust the number of decimal places. Where's it at? There it is. Negative 0.51 and 2.31, just like we had seen on that. And then you can verify them by substituting those numbers back in. 0.51. See, and it's not going to be exactly 0. See, when they substitute this negative 0.51 into the equation and take it to the 4th power and to the 3rd power and squared and over here, it ends up 0 equals 0.03. Well, that's because we rounded it. That's very, very close. So we know, okay, that's probably the solution. If we take one more decimal place and we substitute negative 0.507, it'll be even closer to 0. So these are the approximate solutions because we rounded them. Once we round it, we don't have an exact solution. That's why it doesn't exactly equal 0. There's another one you can do. I'll leave that for you to do. To the nearest hundredth again. Graph that. the third degree, so you know what it's going to look like. And I'll leave that for you. All right, let's look another page. Average rate of change, increasing versus decreasing, minimums and maximums. Okay, that's another thing that we can look at. Let's not use that graph. Let's not do that. Average rate of change. So let's go to one of these that we've already had. I'll put it up here on paper. If we want to look at the average rate of change, you generally choose 2 points. It'll say, okay, what is the average rate of change? We'll use the red graph here. Average rate of change when between, because it'll say between, when x equals -4 and x equals -1. What's the average rate of change between x equals -4 and x equals -1? So what is the value of the graph when x equals -4? It's right here. What when equals -1? It's right here. So you have this point, which is -4, -8, and you have this point, which is -1, 1. So it wants to know the average rate of change is another way of saying the slope. And it wants to know the slope between those 2 points. So I'm going to grab my ruler. So it wants to know the slope between these 2 points. From there, what's the slope of that line? That's what it wants to know. What's the slope of that line? Well, there's multiple ways to do that. We have the slope formula, which is slope equals y2 minus y1 over x2 minus x1. So if we say this is x2 up here and x1 over here, we can do the formula and say the slope equals 1 minus -8, because that's the y values, over -1 minus -4. So 1 minus -8, which means 1 plus 8 is 9. -1 minus -4. So -1 plus 4 is 3. So the slope is 3 because 9/3 simplifies. So that would be the answer. Slope equals 3. That's the average rate of change, 3. We can also look at the graph. What's the rise over run? If we take this point and this point, it goes up 3 and it runs 1, 3 over 1. Or we can just use those 2 points. 1, 2, 3, 4, 5, 6, 7, 8, 9. The rise equals 9. The run equals 1, 2, 3. Again, rise over run. We get the answer of 3. It's just saying take those 2 points when x equals -4, when x equals -1, and figure out the slope between those 2 points. It doesn't matter what the graph did. The graph went up over here and it curved over and went up again. We don't care. We want the average slope between those 2 points when x is here and x is here. That's what it gets down to. The other thing it talks about is increasing and decreasing. For this red function, this is increasing, x increasing. It's still increasing right here, just a lot less. It's barely increasing. And so this is increasing the whole time. Increasing the whole time. When is this increasing? From -infinity to infinity. That's when this is increasing. This one is different. In fact, let's go to this one because this paper's getting full. We're going to use the green one. Ignore the red one. When is it increasing? It's increasing, and we always talk about the x's. When the x's, as the x goes that way. This graph is getting bigger. It's way down here to negative numbers, negative infinity, although it keeps getting bigger till it gets above 0. And then it stops increasing. It stopped increasing right there. We're going to say that's about, let's see, it's increasing from negative infinity to negative 1.5. Increasing. Negative infinity. That's a terrible infinity. That's better. Negative infinity to negative 1.5. And then it starts increasing again when it gets down here, as we drew it. So when it got to 0, x equals 0 right there, it increases again forever. That's the areas where it's increasing. Now, what about areas where it's decreasing? Well, it's decreasing in between there. See, it goes down. It goes down. So decreasing is between x equals negative 1.5 and 0. So this is the interval where it's increasing. This is the interval where it's decreasing. So if it asks for those intervals where it increases or decreasing, you write it like that. All you're writing is the x values. Notice there's no y values in here. The y values are what is increasing. The y values are increasing from negative infinity all the way to negative 1.5. And it's okay to estimate that. If you have it on Desmos, you can say to 1.4863 or whatever, exactly. But 1.5, it's okay to estimate the areas where it's increasing or decreasing intervals. All right. Was there anything else they looked at on that? Minimums and maximums. We can, that's simple too. Whatever this point is right there, that's a maximum. That's the biggest in that area. That's the biggest point. Whatever this point is, well, this one we know was 0, -2. That's a minimum. It's a minimum because in that area, there's nothing smaller. That's as small as it gets. Maximum, minimum. So that's the things that have you look at. Average rate of change, just between those 2 points. Like between that point and that point, the average rate of change is 0. It doesn't rise at all. So this wants the average rate of change between x equals 0 and x equals 2. So I'll leave that one for you to look at. X equals 0 right there. X equals 2 down there. So see if you can figure what that is and then check your work. They got your answer for you. And then again, it reviews translation. Here's our lesson summary. So we're at the end of the lesson. That's good. We've used a lot of time today. Has this graph again, this little table for you to use in your notes. If it's an odd degree, the ends travel in opposite directions and it based on positive or negative, which way they go. If it's an even degree, they go in the same direction. Positive or negative tells you which way they go. And then average rate of change, there's that formula. Talks about increasing versus decreasing, minimum, maximum translations. There you go. And you can print that if you have a printer for your notes. Okay, they give you a couple of pages of practice problems as usual. So you can see if you understand before it counts. It says graph is by function. Describe the end behavior. It wants to know the end behavior. Check your work right there. All right. A bunch of problems. I'll skip all those problems. Let's look at the assignment. Given this function, x to the third, what is the result function when f of x is shifted to the right 1 unit? What would we put in there for x? Would we put x plus 1? Would we put a plus 1 at the end of the function, put a minus 1, or put a minus 1? If we want to go right, there you go. I'll give you an answer. You'd put in an x minus 1, and that would shift everything to the right. All right, so you got 5 problems. 5 problems. Look, I'm going to submit that one answer. That one answer is, it's right. Then you have the practice test. There's practice test instructions, which will have a review if it ever comes up. Yeah, there's a review of the lessons that we did. And then here's the practice test. The practice test has a lot of questions. It always has more than the test because it wants you to have plenty of practice. See, these first two are very similar. What's the quotient when you divide this by that? Remember, we were doing long division and synthetic division back at the beginning. You could do synthetic division with this one. All right, how many problems are there? 24 problems. 24 problems. And then after you do that, you can look at my video that'll explain all those problems if you got stuck anywhere. There you go, 34 minutes and 50 seconds. Don't want it to play. 34 minutes, 50 seconds. And of course, you can maximize that to take up your whole screen and make it easier to see all those problems I'm working on paper. All right. Well, happy Halloween, everyone. I just had Miss Dean brought me a little ghost with candy in it. She set it on my desk. So hopefully you get you some good snacks, some good candy, some treats today. Spoil yourself a little bit. It's Halloween. Enjoy your other classes. I've got grades updated. So for your grade checks, that should be all current and everything in there. So, all right, guys. This is a B-Day Friday. So I'll be here Thursday and Friday if you need help with anything. Make sure your grade's above 70%. Most of you are, if not all. You're very close. So we'll see you guys later on. Happy Halloween.